Welcome once again. So here we are in the lecture series of digital electronics, and in the previous lecture we have learnt about the basic concepts of zeros and ones, and also we have introduced the logic gate concept, and we are using logic gates for solving the Boolean algebra. Now here we will further elaborate the logic gates here. Now there are different type of logic gates: OR gate, AND gate, and NOT gate. This we have discussed in the previous lecture as well. So these are commonly known as the basic gates. So this kind of logic gates, OR gate, AND gate, NOT gate, this we call as the basic logic gates. And we have other logic gates which are basically derived logic gate. So NOR gate, NAND gate, XOR gate, and XNOR gate. So all these are made out of these basic gates only. For example, NOR gate is OR gate and NOT gate. So if we combine them together, then we get NOR gate. So here in this lecture, we shall be discussing further on OR gate, AND gate, NOT gate, NOR gate, and NAND gate. For XOR and XNOR, we shall be having a separate lecture. So OR gate, this is the symbol of OR gate. So minimum 2 inputs we have in OR gate, and we can have multiple inputs, but we can have only one output. And here this is read as Y is equal to A or B. So this is Boolean addition, and we are naming it as OR operation. OR operation. So from the transistor point of view, now here it is the bridge between the analog electronics and digital electronics. So these gates, all the gates are made up of the transistors. So transistor in this particular configuration, if we have, then we can make the OR gate. So in this transistor, through base, we are providing one input A and another input B. And if we are taking output from this place, that means at the emitter, if you are taking the output, then we are getting output as Y equal to A or B. However, if we take the same output from the collector side, then we will be getting A or B bar. So this is basically OR and NOT operation. So this is actually NOR operation. So the truth table of OR gate, so we can understand with a good example of a lamp. So here we have two parallel switches, and this lamp will be on if switch A is closed or switch B is closed or both are closed. This lamp will be off only when both the switch are open. So if the input A and B, these are both zeros, then we can get output as 0. Otherwise, if any one or both the inputs are at the high state or one state, then output we shall be getting 1. So this is the concept of OR gate. So this diagram is very important, because as I mentioned, this is the bridge between analog electronics and digital electronics. So how transistors are used to make the gates, and in digital, further whenever we will be discussing the digital electronics, we will be discussing on the basis of gates only. We shall not be discussing it on the basis of transistors. Now next is AND gate. So in AND gate, we can have multiple inputs, minimum 2 input or more we can have, and we can have only one output. So output of AND gate is A and B. So A dot B is performing Boolean multiplication operation. So here this is the transistor configuration. So we are providing the inputs A and B to these two transistors. That means here if you see that one transistor's emitter is connected to the collector of the another transistor, and then output we are taking from the emitter of the second transistor. So then we are having output Y equal to A and B. But if we are taking output from the collector of the first transistor, then we are getting output as A and B followed by NOT. So this is called NAND operation. So once again we can explain this with the help of a lamp. So here we have two switches connected in series. Now this lamp will glow only when both A and B, both the switches are closed. Either of the switches if open, then this lamp will not glow. So from the truth table we can see either of the input if it is zeros or both the input is 0, then output we shall be getting 0. We can get output equal to 1 if and only if both the inputs are 1. Otherwise we can never have output as 1. So the lamp, glowing of the lamp is indicating one output, high state of the output. So next is NOT gate. Now NOT gate is the only gate where we have a single input. Single input we have, and output we are getting as the complement of it. So here the combination is, here we have only one transistor, and if the input is connected to the ground, we'll be getting high state output. So this is plus VCC. So Y equal to A bar. So that means at the input, if we are providing 0 voltage, we are getting output as VCC, and if we are connecting it to VCC, then output will be getting ground. So this is the truth table of NOT gate. So as I have mentioned, 0 is indicating ground and 1 is indicating VCC. So input if we are getting 0, output we are getting 1. So ground, if we connect the input to the ground, we will be getting output as VCC, and if we connect it to VCC input, then output will be getting the ground potential or 0. Next is NAND gate. So NAND gate is AND gate followed by a NOT gate. So combination of AND and NOT gate. So this operation Y equal to A dot B bar. So complement of AB. So this is the symbol of NAND gate, and here this diagram earlier also we have seen. So this is the transistor based diagram for the NAND gate. So this is the NAND output. So if we are taking the output from the collector side, then we can say this is the NAND operation. And the truth table of this is saying if we have any of the input as 1, then output we are getting 1. If we are getting both the input as 0, we are getting output as 1. So we are getting output as 0 if and only if both the inputs are 1. So either of the inputs or both the inputs are zeros, then output we shall be getting 1. So this is just the opposite of AND gate. So or we can say it is the complement of AND gate. Next is NOR gate. So this is the symbol of NOR gate. So NOR gate is nothing but OR gate followed by a NOT gate. So here output we are getting OR complement, and here also we have minimum 2 inputs and we can have multiple inputs also, but output will get only one output. So transistor, using transistors we can have the same arrangement of the transistors, and if we are taking output from the collector side, then we are getting the NOR output. So truth table, this truth table says that either of the input if 1 or both the inputs are 1, then output will be 0. Both the input if 0, then output will get as 1. So compared to NAND gate, see here, when we have both the input 1, then output is 0. and here when we have both the input 0, then we have 1. So it is the complement of the OR operation. Now this NAND and NOR gate, they have the unique property, and we can realize any of the basic gates using NAND and NOR gate. So that is why this NAND and NOR gate are called universal gates. So regarding this universal gate, we'll be having a separate lecture, and in next lecture we shall be discussing about the XOR and XNOR operation. So we end here. Thank you very much for listening.